This is my final for the lab portion of Electrical Engineering 370. The problem I chose to do is regarding digital versatile disc players. This part just describes the different control tasks incorporated in making a DVD player. Below we're given a transfer function which basically compares or relates the radial pickup position, the coil input voltage, and throughout the problem we're going to be tasked with designing different compensators to improve the DVD player's performance. So for part A and B, we just had to plot the root locus and then again do it in MATLAB if we didn't do it initially. I did. The code for doing so is on the left hand side. I prefer to code my transfer functions in the array method, and that's why I had to calculate the long coefficients to the denominator. You don't have to do it, it's just the way I chose to. On the right hand side you can see the root locus plot. For part C, we had to find the range of K for closed loop stability, the resulting damping factor range, and the smallest settling time. So on the left hand side you can see the point selected where the root locus intersects with the y-axis. We get a gain of 0.0322, which on the right hand side that's how we got K is greater than 0 and less than 0.032. The poles our dominant closed loop poles are at the top. They're negative 4.38 plus 243i and negative 4.38 minus 243i. At the first one, the damping ratio is 0.02, and so our damping ratio range is 0 is less than zeta is less than 0.02. The natural frequency is the distance from the origin to the closed loop pole, and that is 248.96, which gives us in the equation for our settling time at the bottom there, we end up with 0.8 seconds. So part D, design a notch filter compensator so the system's dominant poles have a damping factor of zeta is equal to 0.7 with the closed loop settling time of 0.1 seconds. So to create a notch filter compensator, the first goal is to arbitrarily place zeros close to the dominant complex poles. And so I place them really close. I place them at negative 3.56 plus 249i and negative 3.56 minus 249i. And then we also have to place two poles on the real axis far away from the origin. So I placed one at negative 30 and one at negative 80, which the root locus for is, or in the code for such, is on the left hand side. At the point selected we ended up with a gain of 0.00631, which corresponded to the desired damping ratio. Part E, simulate the system step response for part C using MATLAB. So there is the new system equation essentially, and there's the step response for it in the code to do so. And there's a step info rise time of 0.0319. It has a peak time of 0.054, but its peak is only at 0.5711, which isn't desired. And so it has quite a bit of error. And so we end up with a 12.7% overshoot, and yeah, it's most of the important information. For part F, we have to add a proportional integral compensator to the system to achieve zero steady state error for a step input without appreciably affecting the transient response achieved in part B. So for this part, for a proportional integral compensator, add 1 0 at the rightmost pole that was added in the last compensator, and so I added the 0 at negative 30, which took out the s plus 30 in the denominator. And then we also have to add a pole at the origin, so you add an s to the denominator. Once again, plotted the root locus. I don't have it in that graph, but I selected the point corresponding to the 0.7 damping ratio and ended up with a gain of 0.00518. Part G, simulate the system step response for part E using MATLAB. Here's the step response in the code that I used to achieve it. There's also the step info. The peak time is significantly longer than the last one, however, it does reach our desired value and our desired steady state error. There's no undershoot, overshoot of only 3.1%, rise time of 0.0565, so only 0.02 more than the last one. I would say it's a pretty good response. And so that was the last part. Here is the final code I used to execute the whole project, and that was it. Thank you.